Hello, my name is Marco Kellner, and this is my Modern Physics Lab number 2 for a motion of a falling object. Introduction. The problem was to observe an object falling from rest and watch its displacement over time, then to make a computational model using BPython that models the falling object with and without drag force. The result was that the computational model is very similar to the captured motion, but it overpredicts the ball's position by a little bit. When the drag force is added, the model almost seems exactly like the observed motion with minimal discrepancies. This is the video of me dropping the ball that I used for this experiment. And here I have put it into tracker, and I have to tilt the axis a little bit because the table the camera was on was slanted a little bit. Each dot that you can see on the ball is me manually clicking on the ball's pointed center of mass. And then tracker gives us on the bottom right corner a spreadsheet of the ball's position over time. A quick reminder, in this lab we use Newton's second law, which equals force equals mass times change in velocity divided by change in time. The final velocity equals initial velocity plus net force divided by mass times change in time. This will help us find the final position of a moving object, which equals initial position plus final velocity times change in time. Some other relevant equations. The force of gravity equals the m times g times -1. M is mass and g is, here on Earth, is 9.8 newtons per kilogram. It is times -1 because the ball is going in a negative y direction. Also, we'll be using drag force later on, but it is b, a constant I found using trial and error, times the ball's velocity squared. Here's the VPython code that I used. Here I specify ball.m is 0.907, which is the mass in kilograms. The ball's position is set to be 0, which is the origin of the calculation, and ball.vel equals its initial velocity, which is 0, because the object that we're dropping is at rest. And t equals 0, so that's when we start our clock. The other initializations, I used a very small delta t so it can give us a very accurate calculation. And then I specified g equals 9.8, because here we're on Earth. And j hat just specifies as the direction of the y-axis, and there down here is b equals 0.1144. That is the constant that I found using trial and error. Here's the calculation loop. Because my video only ran for 0.533 seconds, that's how much my loop will run for. W equals the downward force due to gravity. And then Fd is the drag force, which I don't really use until later on. So I comment it, and the Fnet would only equal W and not plus Fd for the first calculations. Later on, I actually use it. So here's where I insert Newton's second law. Is ball.vel equals ball.vel plus ball.vel plus Fnet divided by ball.m times delta t. And here is just predicting the ball's position. Ball.pos equals ball.pos plus ball.vel times delta t. And here I specify the change in time for the calculation. Here's how my program will run, my model. The yellow line is the force of gravity, and the blue line right here is the drag force, which is increasing as it keeps on falling and falling. But the gravity is a constant. Here is how it would look in a form of a graph. It keeps going faster and faster, so it goes into a slope form. Here is the graph that I use of experiment versus model with no drag force. The red dots represent the experiment, and the blue line represents the model of the calculation. And as you can see, it overpredicts it by a little bit. So in the calculation, it seems like the ball would be dropping more. In this one, the new line is the model with the drag force. So in the calculations, I actually included the FD line. And as you can see, there's barely any discrepancies because the drag force will equal it out the ball until it reaches where it ended. What does it mean? Terminal velocity in the constants of this experiment means that the falling object will reach constant velocity as it falls. This is because the drag force will keep exerting a constant force on opposite direction of gravity until it cancels out the acceleration due to gravity. In other words, when the magnitude of drag force equals the magnitude of gravity. This would be shown on our previous downward curve graph as a linear slope going down in a graph. In other words, the curve would eventually stop curving and just start going straight. So what if the ball was initially thrown down? Would the terminal velocity be the same? Because the ball is thrown with an initial negative y force, it would reach its terminal velocity sooner because the drag force would be bigger due to the fact that it's crashing against air at a faster rate. If the initial downwards force exceeds the terminal velocity, the ball would start slowing down until it reaches its terminal velocity. This would look like an upside-down parabola ending with a linear slope when it reaches its terminal velocity. In conclusion, as an object falls, air resistance will exert a drag force in the opposite direction of gravity. The drag force will keep getting stronger until the magnitude of the drag force equals the magnitude of gravity. This is when terminal velocity is reached. Some possible discrepancies that might have happened in this lab is the human error in tracking the position through tracker. Because of my camera quality was not as great, it was hard to find the center of mass. Also, the table on which the camera rested on might have been a little bit tilted, changing a little bit the position of the ball. The last thing that might have caused a discrepancy is the B value, which I found through trial and error. The value might have been a little bit higher or a little bit lower, but either way, it was very close to the real number.